Uh, Nobody watching, kind of irritating me. I mean,
I do this channel mostly for me. I just like
yeah.
learning about this stuff that much.
Well, I'm
So
trying to get out to people and trying to, help people understand the problems here. And nobody ever, like, if I were a crazy Christian, like, if I converted to Christianity, and I'm thinking about doing that, just to get viewers, and I mean, I would get like 200,000 views, right? With some bullshit.
I've seen a lot of Christian accounts that it's like, how is this person have
I
this
know,
many followers and this much?
right?
Yeah.
We're
But
wrong. Are we live?
yeah. I just went live. I said I was.
Oh, okay. Oh, well, you don't have an intro, so
I have one, but it's just a pain to set it up, and I have to pay for StreamYard, and I didn't have to pay for StreamYard when I paid an artist to make me a cool introduction, and then now they changed it, so now I just don't bother with the introduction. But I'll get back to it once I get a better computer. It's just taking me a while to get the funds to do that.
yeah.
But anyways, welcome everybody to evolution, enzymes, extremophiles, protein folding, and protein synthesis, and the future of science and technology with T Savo and Austin Sims. And of course, we got Mike from Answers in Atheism over here. And I hope we gave ourselves like 90 million hours to discuss all this because it seems like a lot. But we're going to try and get it done in like 2 to 4. And we have fortunately a great expert here to help us do that. T, you're kind of the star of the show. Most people watching will know who me and Mike are. Why don't you introduce yourself and tell us a little bit of the story? Like you started telling it to me backstage, and I was like, "Man, this is great. We got to save this for the stage." So, T, take it away. Tell us about yourself and your research with Dr. Arnold, and just the amazing discoveries you've made in your life that you were telling me about backstage.
Absolutely. My name's T. I'm a what do we see these days? A data scientist, a glorified data scientist. That's what we're called, right? I am in no way should be mistaken for a biochem researcher. I was just surrounded by them, right? And that's sort of like the fun of my life. I started off doing the .com bubble back when that was a thing, and coding, right? Started engineering the heck out of websites and all of that, and got to a point in my career. I was CTO of a number of core companies, and then got to a point where I was like, I'm just going to do my own thing at this point. And I started working on physics simulations, and the physics simulations led to games, but the games weren't really interesting. The physics simulations were much more interesting. And I thought, what if I could shrink these down, right? What if I could do molecular physics? And it was about this time that I talked to a biochem student who was also a programmer. And he said the most amazing things to me that changed my life. He sat down and he explained to me how life is like a CPU, which I know is a strange analogy, but it actually makes sense when you think about it from a programmer's perspective, from a computer scientist perspective. What he was doing is he was breaking down biology in terms of how a computer scientist might approach it. And this changed my life. This changed my career. Suddenly I was chasing down this concept of an evolutionary framework, right? This idea that computers could evolve solutions. I tried this in code. I tried this in CPU design. I tried this in fluid dynamics, fluid simulations and optimizations for like oil pipelines, traffic flows, stuff like this, where I actually got to the point where I was simulating at the molecular level chemical interactions at the atomic scale, right? And what I figured out how to do was to do this Monte Carlo style. That's tech speak for en masse, right? What we're going to do is we're going to say, does this work? Okay, we're going to keep trying this. And does this work? We're going to go a different way, right? And so we get to now do molecular stuff at GPU speeds. And this is how I stumbled upon, Dr. Arnold, or rather, their team found me. They were working on protein folding, and they wanted ways to accelerate their work. They understood how to code. They got it. They were biochem students who were programmers. They knew this stuff way better than I did. But what they didn't know was they didn't know GPU programming. They didn't know CUDA, OpenCL, how to take their code and massively parallelize it on a GPU, like they do with Bitcoin, right? And so the whole idea here was I came in as a technical consultant that eventually became the technical lead for the project. Francis Arnold proceeded to simulate massive amounts of protein folding chemical pathways, if you will, right? And from this, she won half of the Nobel Prize for Chemistry in 2018 for a novel method of protein synthesis. And they don't list all the consultants that they hire along the way, right? I was just the guy who helped the actual biochem guys to get to cloud scale, to take their $3.8 million that they raised in grant money and turn that into a GPU farm that could fold proteins.
That is so cool. That's and now look at where it's at today, to where there's AIs that make proteins for people. That wouldn't be possible probably without Dr. Arnold's work and your insights specifically adding to her work. That's incredible.
We were pioneering the field at the time. And that's the first thing that you posted on Facebook, you posted on a science group, and somebody immediately came in and pointed out AlphaFold figured this out. And for me, this was the most amazing and the most humiliating, or humbling, I should say, moment of my life, because they make my work look primitive. They make my work look caveman-esque.
That happens so fast in science today. Right. It used to be, it took like 300 years before somebody was standing on Linnaeus's shoulders. Somebody was standing on your shoulders in like 30 months.
Oh, man. At the time. Now we're dog water, as they say.
Yeah. No, but that's still incredible. It still absolutely blows my mind. And that's such a cool story that you just happened to be programming things because you had heard this interesting model. And oh man, that's so cool.
Right. And I can't take the credit for because they did the work, right? They are the ones who took it to the lab. They are the ones who ran the simulations. My job was to help them get it to GPU scale. Right. Yeah. And that was a major booster for them. That was a huge up, if you will. Right. But so it's not like I'm not the guy who won the Nobel Prize. I'm the guy, the code monkey. Right.
Yeah.
Who behind the scenes helped a bunch of really smart people do what it is that they did. Right. I'm way down the ladder on this. I don't want to come across as like I'm some biochem expert and I can tell you everything. That's not the case. I'm a code monkey.
Right? Yeah, I listed you down as a computational biologist. Right. I don't think I even put down that you were the tech lead. Like maybe I could add that to the description, but no. I focused more on how you pivoted to being an entrepreneur now. Scott Duke. Hey, how's it going, Scott? He has a question for us. How do researchers measure how accurately simulations reflect reality? Have simulations ever required scientists to update their models of reality because they capture some aspect not previously considered?
Yeah. That's exactly what our work is about, right? So our work was trying to find chemical pathways that led to certain outcomes in protein, in folded protein, right? And so what we would do is we would simulate en masse what they were trying to do in the lab. And then, having gotten the results, that would be filtered by rank. We would only be interested in things that had a high probability of outcome, right? And then we take that, we have to take it to the lab. We still got to do the work. We still have to, and this is where, like, I'm not even a part of this any longer, right? They're off in their own little worlds at this point with chemicals in the lab, figuring out where the simulation doesn't meet reality. And that happens a lot, right? It happens a lot, and it happens less and less over time, because what we would do is we would have unit tests, and we would run the unit test to see, does hydrogen bond to hydrogen? Can we form water, right? Can we get an autocatalytic chemical reaction going, right? And so if any one of those unit tests failed, or any time that our simulations failed to match reality, which happened a lot, right? We would go and we'd write more code in order to ensure that moving forward, that didn't happen again. And then every time we went to deploy the code, part of the integrated process of deploying the code was running all of those tests, running the can we make water test, running the can we fold a protein test, which sometimes took hours just to run all the tests, right?
So I'm hearing that it's a combination of trial and error, and then you have a couple of heuristics, and one that's specifically way more algorithmic, the specific test that you will run.
Because at the core, we have a simulation of chemicals falling into lower energy states, and that's what we're trying to parallelize, right? Because the result of that is a new macromolecule, if you will. That's what we're talking about. We're talking about a new way in which the protein folded, or a new set of chemical bonds that occurred along the way. And now we have a new state that we want to explore the possibilities of. And so that's a parallel problem that we can explore in parallel with more GPUs in parallel, right? We can fire up a GPU and fire up another GPU to say, let's try this path, let's try this path. Okay?
Wow. So did you have like separate profiles for each amino acid as to how they would fold, and
as to
some sort of
activation states, their energy states, their all of, and then what catalysts are involved in. And so what we're doing is we're computing literally eigenvectors to try and figure out, do these chemicals bond first and foremost, all right? And are we going to form a new nucleus, if you will, right? Which is a way of saying that we've got a bond at this point, right? And so instead of treating it as two separate units, we're now going to treat it as one computational unit to move forward with, right? And this was one of the major breakthroughs, was in how to model how chemicals come together, and then make branching parallel paths off of that, right? When a chemical breaks, we're going to break that apart. We're going to create two computational states. When we bring them together, that's one computational state, and then we're going to branch off different pairings off of that, right? And so that was like, they had this figured out.
Yeah. So you're talking about programming life in addition to programming the specific evolution that they're trying to isolate in this simulation.
Right.
Kind of a little bit.
And so they had already. They just didn't know how to do this at GPU scales. They didn't know how to take this and then take it to the cloud and then massively parallelize it on the best possible hardware, right? And so that was the breakthrough, was like, coming in and going, okay, we got to write a shader, right?
Yeah. Well, so what size proteins did you work with?
All the way up to 100 in length, right? We started with like 19 is like our examples, right? Those are our unit tests.
100 amino acids in length, right? I want to make sure I'm using the right unit.
Sorry, amino acids. We start with, can we do a hairpin turn, right?
Okay, yeah.
Like one unit test right there, right? And then we start to, so as far as proteins go, we would only work one protein at a time, right? Our entire simulation was focused on a single protein that consisted of a bunch of amino acids and how we were going to get that to fold in a certain way, right? We
Yeah,
didn't
yeah.
have protein-protein interactions of any sort. We were just looking at the enzymes and how the synthesis and transcription actually worked, right?
Right.
So
We're trying to solve the problem of enzyme evolution, which is how a protein would fold in such a way that it has the activator space that is
right.
characteristic and diagnostic of the type of protein that we classify and categorize as an enzyme.
Right, because we would start with an autocatalytic simulation. We'd say, hey, how do we get to enzymes, right? Enzymes form these things. They're cool little machines. Imagine like a 3D printer that can print out parts that are parts for 3D printers, right? And once you get to enough of these things, they start to grow in size. They start to autocatalyze into their own domain, right? And so this is like, can we get an autocatalytic chemical solution going, right? And then once we do that, we're starting to say, okay, now what we want to do is we want to take these amino acids, link them together, and figure out how they fold, right? We want to get them to work together and figure out what the final configuration is that are the most chemically likely, right? Because chemicals, here's the cool part, chemicals want to fall into lower energy states. And in doing so, they form more complex macromolecules, right? And those more complex macromolecules, that's what we're looking for. We're looking for how can we go from this high energy state to this low energy state and achieve what is the configuration that we're looking for, right? And so if we can find these particular pathways that lead to these particular states, that's a shortcut, right? That's a process that we didn't have before that gets us to something that we sort of need, which is a full protein, right? And so that was what we won. That was what she won the Nobel Prize for, was a novel method of protein synthesis, which results in us being able to dial up proteins in hours to days instead of weeks, right?
That's super cool. Yeah.
That was the major breakthrough, right?
So did you predict enzyme function for these proteins? Did you work with metal ions at all?
Absolutely. That was the whole goal of the simulation.
So what's really interesting in evolution is not the huge proteins, but the small ones, and like how you could take a random group of, just randomize a bunch of amino acid sequences, small ones, right? Like 19 to 50 or whatever, 40, and find motifs. So basically active motifs that will do some enzymatic reaction. Did you work with that?
We didn't. I understand that they did later, after my part, right? That was like the next step and where they wanted to go with research, right? But I was gone by then, so.
Yeah, because a lot of this happened with really smaller molecules, right? Smaller random sequences, and that's how the protein families started to come up. Like an active functional protein now will have like 7 motifs, and each of the 7 parts will do something. One will grab some DNA, another one will grab some ATP, and that is very, very interesting and powerful in figuring out this evolution problem that we have before us. So that's pretty cool. Yeah,
they're like 3D chemical machines. They are little self-replicators. They're like nanites from Stargate, right? They take what's around them and then make them into more things like them. And it's just a very, very cool process. And so we turned, at the time, what was largely trial and error in biology into GPU scale computation. That we can figure out what's likely, and then from there, and that's the whole point. It wasn't just, and then our process is also trial and error, because when we get processes that look likely, and then we go to the lab, and they suck, they don't work at all, right? That's a problem. We have to go back to the code and figure out where we went wrong. And that was a fascinating process, to be constantly humbled by reality, that no matter how good your simulation is, it can always be a little bit better, right? And that's what modeling problems is. A model is always necessarily removed from the thing that it's modeling. If it weren't, it would be the thing it's modeling, right? It's just some models are more useful than others. What we're trying to do is we're trying to build a more useful model.
So we have our first live chat comment, Mike. If you can hold on to the point you want to make for a second. And I want to read it because I think it's touching on something you said you wanted to talk about, T, molecular geometry. That's what it's called. Oh my gosh. It sounds so complicated in just the name of it. But Oceanus Helios, the man whose name is two dead gods, says many proteins are composed of structural alpha helices and beta pleats. These portions aren't the active portions of those proteins, so 100 amino acids isn't a large protein.
No.
That's correct, right? And that was part of the problem that we ran up against, was scaling, was how to get to larger proteins and how to scale the solution. And that's where diffusion came in and kicked our ass, quite frankly. I mean, that's where alpha says, oh, look, we've got a better way of dealing with this, of this scaling problem, right?
So one of the smallest bacteria is Saragossa 11, found in the nutrient desert of the Saragossa Sea. It has one of the smallest genomes too, and is the least complex. This is bacteria.
Yeah. So what programming language? I know nothing about GPU programs. I'm a C Ruby programmer, C Ruby JavaScript consultant, like 40 years consulting, but I've never worked on GPUs. My son has, but so do they have their own proprietary assembly language, or do you use C or C++, or what do you code in?
We started out in OpenCL, which is a compiled language, and then we moved to CUDA very quickly.
Okay. So is OpenCL pretty low level like C, or is it?
They're both pretty low. They're both very C-like, I would say.
Okay.
Right? Okay. But it's exactly how you would expect it to work. The idea is that you get X number. You can just define, some processing unit of X and Y size, and then each unit is a singular program, and then you get to duplicate that program across your entire chunk size, right? And then the data is the thing that changes, right? So underneath, that's the thing that's changing each time. So what you get to do is you define a block of 256 by 256. It's one program, but it's operating on a vector 256 by 256 and mutating the vector. It's changing the vector. And so what's changing underneath is the program itself. And then within the program, you get to sort of, read the data and do branching and all the things that you would expect to do in a C program, right?
Cool. Yeah.
And so you have to figure out how to start with, a small number of a small, nucleus that you're working with, and then you want to branch that into more nucleuses. And so initially, there's shaders that are sitting idle. During your first couple of chunks, you're building out the simulation to be processed, right? But then that quickly gets, becomes a exponential problem, right? It quickly grows and grows and grows, and you start running into the scaling problem, right? And this is where diffusion kicked our butt, right? Diffusion shortcuts all of this. It goes, let me imagine a vector space that sort of looks a little bit like the final result. Now let me imagine it looking a bit better, right? Now let me imagine it looking a little bit better, right? And that's like a much better way of just getting to the final result rather than trying to figure out how to scale out that growth pattern, right?
cool. Okay,
So-
one more thing before we get into the molecular. You says you did physics simulation for gaming, like physics engines.
Yeah, that's where I got to start. Yeah.
Okay, so there's in embryogenesis, the development of the embryo. What's been driving me crazy is that there are gamers out there. What we need is a soft body physics engine that represents cells and how they communicate and how they push against each other and how they can split apart and move and do all of this. But do you know of anybody that's doing that work in how embryos develop, basically? Because, okay, that's something I'd love to have a
problem, right?
I know.
It's just really, really hard, right?
I know every time I try to do it, of course I'm an idiot. I try to do it in C or Ruby or Python, but every time I try to do it, I run into just so many parameters and stuff. But anyway, I'd like to have a private conversation with you sometime about that to see if there's anything, if there's any way, because if there is, that is the magic that's going to detail how certain organs developed and evolved. Basically, that's one of the keys to evolution. So that's a big deal.
The solution there is going to be a hybrid approach, right? You're going to have some sort of model, which is modeling in a transformer diffusion, whatever it is, way how cells work. Then you have some sort of like traditional simulation, if you will, right? And then that's the thing that's controlling the interactions, right?
Yeah. And basically the cell changes, and then the cell and its environment tells the genome what to do next. And then, it goes on, and so it becomes, it's pretty cool.
Yeah.
Anyway, okay.
We have an audience question from Alan Ursel. Can you talk about statistics? Can you make the question a little more specific, Alan? Are you just asking a general question about statistics? Is the study and analysis of data? Like what is the question? Do you understand what he's asking?
Statistics. I know exactly what they're asking, because statistic underlines the entirety of the model, right? What we do is we want to create a pruning function that is statistical. It's some sort of heuristic that says this pathway is no longer worth considering. And so you want to talk about what are the odds? Like, think about rolling the dice, right? What are the odds that this particular chemical pathway or this particular combination of dice is going to come up? Those are the ones that we're most interested in. We want to follow when we want to reduce the solution space, which we have to do because not all chemical pathways are relevant. We're not only expanding that solution space in a statistical way, we're reducing it in a statistical way too, right? And so everything is powered under the hood by statistics, right? And that's true in a transformer diffuser model, or a GAN, or any one of those, right? It's all about how entropy works. And if you think about it, it makes sense, right? Entropy works by following this distribution curve, and it just tends to be up here, right? You might see a little bit of variance over here or over here, but you're not going to see any variance over here or over here. You're not going to see a balloon full of air that suddenly has all the air on the left side and a vacuum on the right side. You're not going to see it. It's possible, but it won't it's not statistically likely. And so those are the types of scenarios we don't want to chase down. Does that make sense?
Yes, absolutely. We're defining a possibility space using statistical reasoning, and we're also defining like heuristic diagnostics by statistical reasoning, saying here is where we consider this a no longer worthy pathway, was how you put it, basically.
Yeah, no longer a pathway that's not worth considering, not worth computing. We want to reduce the solution space to make way for new chemical pathways that we're exploring, right? Yeah. And then we can stop when we get to the solution. And then what we want to do is we want to define how much work do we want to do before we just give up and say we're not going to get there, right? It's all statistics.
Oceanus Helio says, I can see a huge problem with computer simulations. Molecular orbital theory. This will change the degree and reactivity of active site portions of proteins, raising and lowering reactivity. It took a supercomputer to model everything that is going on within a ribosome.
Yeah, that's exactly the type of problem that we ran into right away, right?
Yeah.
And that's the type of thing that we have to statistically correct for. And so it's all about, and that's why the statistics question was so relevant, is every time we come up with against one of those problems, the solution is to figure out how do we adjust the model to be more like reality, to match reality more often, right? When you roll the dice, you want to see it, what your model match what the dice roll gets you, right?
Yeah. They also asked, as a beginner, I have another question. Will you consider statistics a branch of STEM subject? 100%. Yeah. Statistics is the science of data. Yeah. It's for sure science.
100%.
Yeah.
If there's two things you should learn, it's statistics and molecular geometry. Those are the, if you want to go into biochem and really do cool work, and and especially with computers in biochem, statistics and molecular geometry, it's where it's at, right?
Right. Well, that gives me something to consider in my coursework that I'm going through right now, for sure. And so we've kind of talked about what are enzymes and how we use technology like programming and bioinformatics to study enzymes. What is the data that we have that indicates they evolved?
So we could see it happen, like when we take, for example.
Oh, that's a very interesting answer.
Right, we could actually, like, when we're running the simulations, we could literally watch this happen in fast forward. We'd simulate mutations and see how one enzyme could gradually shift its function while maintaining that self-reproducing capability, right? And that was the critical moment for us, was like, oh, look, this was the thing we were trying to get to, and it got to it. How? Let's trace back through simulation the chemical pathway that it took. Now that we know from tracing backwards, now let's go to the laboratory and let's start from there. And we're going to try and get to there using that same chemical pathway. And that's what we're trying to do, is because normally this would be like, you got two options. You got trial and error, you got educated guess. Like, how do you do better than trial and error, right? And that's where you're going to induce some, I don't know, statistical modeling, for example, and that's going to lead you down a certain path. Well, what we're doing is we're doing statistical modeling at GPU speeds in order to arrive at the most likely solution.
So you're saying you experimented with proteins or enzymes, rather. Well, proteins that became enzymes, or
not that became enzymes that became more enzymes while maintaining their ability to autocatalyze more enzymes. That's the critical part. You can watch this happen in real time. Is enzymes have this cool ability, right? They have this ability to make more enzymes and shift their function while making more enzymes. That was the moment for us, right? Where we said, oh, wait a minute, these things are doing something else in terms of their functionality, and they're maintaining their autocatalytic capabilities of making more enzymes. That's cool.
You saw that this change had developed.
Yeah.
And then you created a simulation trying to model how it happened. And then you went back and you, based on what you gathered in your simulation, you actually synthesized the protein. Wow. Okay.
Yeah, that was the cool
I can see why you would win a Nobel for that. That's freaking amazing.
That was why they were brilliant at what they were doing, right? Is they actually understood how amino acids work, right? How these things worked with enzymes in order to make these different structures. And what we could do, and this is the cool part, right? is we could turn up the temperature. And that was really interesting, right? Even more interesting than doing this at like, varying degrees of, above and below room temperature, like turning up the temperature, doing it at like 105 degrees, 107 degrees. That was the very interesting part, because they still did it. They just did it through different chemical pathways, right?
Really?
That's really cool.
Yeah,
Wow.
and that was the cool
So that we're going to talk more about that later. We're going to talk about some how that might relate to what are called superthermophiles and extremophiles, these cool little organisms in nature. But okay, that is super cool. I did not know exactly that the evidence that enzymes had evolved was like that, was something we had, predicted, recapitulated. That's really cool. And you're talking about how proteins become what they are, and that is like you're saying that is like the bleeding edge of like
right there.
chemistry, biology. It's one, and what I'm thinking is, because proteins often fold incorrectly, this is a big reason why we want to understand the protein, because when it does fold incorrectly, it causes all kinds of diseases in humans. So not only is this work super important in terms of like understanding evolution, it's also like medically very important. So for sure, I can see why this got so much funding and why it won a big prize. That's really, and it's amazing that you guys actually made steps with it. That's very cool.
I don't want to understate the case, but this is very important. Enzymes are the way that our whole biology, our whole system does things like stop bad, incorrect folding. Right? There are enzymes for that. It's like an app store. There's an app for that. There's enzymes that, and here's the thing. And if you want an analogy, you can think of this as like an assembly line, right? But if you fold the enzyme incorrect, if you fold the protein incorrectly, that's like giving the assembly line worker blade hands when they're asked to perform a very delicate job, right? That's the correct analogy. That's the right way of thinking about it. And so these people who now have blade hands, they're trying to do a delicate job, and they're chopping shit up instead, right?
Yeah.
And so this is a really critical part. The better that we can understand enzymes and their role in protein synthesis and protein folding, two separate processes, right? And that's a really important part, right? There's protein synthesis. This is where, it gets transcribed to mRNA by polymerase. And then after that, that becomes a blueprint, right? And then from that, you create a new protein through a different set of enzymes, right? And so it's these enzymes that are working in conjunction. One has to break apart the double helix. One has to copy it into another double helix. One has to assemble it, snip it off at the right time, right? That's a really important part, because that's telomeres. Cancer is caused when telomeres get out of control, right? And so the better that we can understand this enzymatic process of protein folding, the better that we can do things like cure cancer.
Yeah, 100%.
Right.
Yeah, that is a fantastic example of what I was talking about. Mike, what do you think Sal Cordova would think of this conversation?
Oh, I didn't know he. Sal Cordova is a creationist nutcake that he thinks he knows. He thinks he's like a big deal in molecular biology, but he doesn't. I had to teach him how carbon atoms worked about 4 years ago, and now he's running around shooting his mouth off about how proteins can't possibly evolve. He's just. And the man, like, he picks topoisomerase, or he has a zinc finger, ZNF136. He picks just one little star protein, and he draws a picture of it, and he says, that can't happen. That couldn't happen naturally. And he's an idiot anyway. So you're just trying to piss me off, Austin, by bringing up cell.
All of us there, right?
Yeah.
I was saying as
Right.
he was explaining what he did to me, it was sounding more and more like he's Sal Cordova's evil twin, but like he's the good version because Sal's the bad one. Yeah.
Yeah.
Right. I talked about it before. I said entropy wants to follow that distribution, that norm of distribution, right? And chemicals want to fall into lower energy states. I'm anthropomorphizing, sure. I'm saying they want to, they tend to, they do. Right, I mean that's just that, like the nature of chemicals is they fall into lower energy states, right? Macromolecules want to get more complex as a result, right?
Yeah. Yep.
Is as these more complex macromolecules form, they're selected for by the environment, right? Either they have some ability or some trait or some capability, some capacity that allows them, this ability to survive in this new environment and offers them some survival advantage. Or they don't. They sink to the bottom. They float to the top. Or they're buoyant and they're hydrophobic and hydrophilic, and they form little globules of fatty molecular acids, right? And this forms, some sort of protocell in which we have a space for evolving chemicals to be protected from the environment. These types of things, these types of chemical evolution, where molecules fall into lower energy states, they get selected for by the environment for their abilities, and as a result, macromolecules complexify. That's just a fact.
Yeah.
There's no denying.
He said the thing, chemical evolution. That's right. You evolutionists, you have 6 kinds of evolution, and you only admit to two of them, and only one of them is real. And yeah.
Then there's the fascinating field of biological condensates, where inside of this, basically inside of the cell, there are these mini or micro organelles that consist of certain proteins that kind of glob together and form their own little chemical manufacturing environment. And they're called biological condensates.
Yep.
And that's something that's just coming of age, and we're going to work on that. That would be the next step beyond protein folding, is protein interactions, and how these biological condensates form and what they do in the cell and the nucleus. So.
And remember, proteins are just one of the 4 biomolecules. There's also lipids, and lipids
we got RNA
form into membranes. So where and when do protein synthesis and protein folding happen?
Okay, so
and I think it's basically near the end of DNA transcription, right? Basically, if I'm recalling some of my science lessons correctly.
Protein synthesis is the process where the cell reads the DNA instructions and it builds a chain of amino acids. Yeah. So you can sort of think of this as like stringing beads on a necklace, right? Then you have protein folding. That's what happens next. So this newly made chain twists and folds into a precise 3D shape that's chemically bonded in a certain configuration. And this forms structures like, for example, hairpin turns and loops and other shapes that are really, really critical for determining the function of the protein itself. Because if you can't do a hairpin turn, you can't do the whole self-replication trick. And so it's proteins of length 19 that we know about that are the smallest length proteins. It could be 18, it could be smaller, but that I personally know about, proteins of length 19 that can actually do a hairpin turn and do the whole self-replication trick. But it was actually proteins like 52, 53 amino acids long. Those were the early self-replicators of life on prebiotic Earth. They were much longer than the 19. And this idea, and this is one of the dumbest ideas ever, that they had to form spontaneously. That's dumb, right?
Had to form on what?
That's one of those things that can happen up and then down, and then it can shrink and then it can grow, and then it can shrink there, or it can shrink and it can grow, and it can shrink and it can grow, and it can get longer and it can get shorter, and it can get longer and shorter and longer and shorter and longer, and finally until we get to that very specific configuration. But each one of those configurations, that's another chemical pathway opportunity to explore. When we're talking about billions of these things all floating around, being chemically falling into lower energy states, and we're doing this over millions of years, right? Eventually you explore those chemical pathways. Eventually you get to length 52, length 53. You get to the conditions of prebiotic Earth, right? It's one of those things that it doesn't have to happen all at once. There's nothing, I really fight against this spontaneous about the process of chemical evolution. Chemical evolution is messy.
It's cumulative, yeah.
Right? It goes up and it goes down. That's what systems chemistry is about. It's about finding states of homogeny, right? And then we upset the environment. We add a little bit of salt to the environment, and it changes the whole chemical state. Now we have to do reverse osmosis in order to homogenize again, right?
So here's an interesting question. Does protein synthesis and protein folding happen outside of like multicellular living organisms or even like unicellular ones? It's just chemistry, right?
That's the study of systems chemistry, right? How do chemical situations go from states of homogeneous to states of instability and then back again? How do they do this, even when we're not talking about the micro scale of inside a body, but the macro scale of over millions of years in an ocean where there's volcanic vents and tide pools that are evaporating and all that stuff? That's systems chemistry, right?
Yeah.
And that's a differentiator from synthetic chemistry. In synthetic chemistry, if you're looking for a particular reaction and then the reaction slows down and doesn't continue in the way that you're looking for, you throw the thing out, right? Yeah. That's not synthetic chemistry at all. In systems chemistry, we're much more interested in what happens when we get to that state of plateau, and then what happens when a change comes along, a change in the environment, and this prompts a new chemical pathway. That's the difference between synthetic and systems chemistry, right?
Yeah, the thing with gene regulatory networks, basically things that, like these pathways, there's like one or two pathways that a protein will participate in that we know about. But then there's all of these mutant proteins and other little molecules, and there's probably like a network of pathways. And when you look at the evolution of gene regulatory network pathways, that's where it gets really cool. But and then the other thing is proteins some proteins start folding right out of the ribosome before they're even done being translated. Yeah. And what effect does that have?
I'm interested in the answer to that question, and I'm also curious if you did say that in nature that things will, outside of a living system, fold into the viable living system shape.
Oh yeah.
Right. Yeah. Absolutely, 100%.
Yeah, because it's like throwing a bunch of magnets together, like these toy magnet things. They're going to stick a certain way based on what amino acids there are. And every amino acid has its own magnetic characteristic, right? And then you hook them together like Legos. So
I have heard that hydrophobic and hydrophilic side chains have an impact on how protein folding occurs, and that is basically because of ionic forces, which is literally electromagnetism. So I think that's a really good analogy. It's a little more than analogy almost.
Let's go back to the assembly line analogy.
Yeah. Okay. Cool.
You've got like 8 assembly line workers, and they're all charged with making a car out of Lego bricks. But there's a rule, right? Once a Lego brick has been placed down, you can't unplace it. You now have to build on top of it. Once they
Yep.
word. There's no unfolding of the protein once it's folded down.
Mm-hmm.
So when so the final form dictates their functionality. So early on in the process, when one enzyme is present and it causes a certain type of folding, that eliminates entire chemical pathways later on down the line. You're done.
Yeah.
The only way that you can get to this particular way is if early on this occurs, right? And now we're going down this path, right? And so
in
that
the
is absent, right? You can go on a completely different path, right?
So in the assembly line simile, the gene is kind of they're the workers, they're the assembly workers on the line, placing the Lego blocks of the proteins.
They are sort of
depending on what piece goes down, it impacts where you're going to put the next piece down.
The genes themselves are more like the Lego blocks and the blueprint themselves, right? They're the car that's built, right?
Okay,
it's enzymes that are the factory workers that exhibit the force that cause the Lego blocks to link together, right?
Yeah.
And this is why it's so important to understand the role of enzymes. Is they're the ones who their presence will cause this Lego block to link to this Lego block, and their presence will cause it to not happen, which leads to a completely different chemical pathway.
It's like a Lego block of a distinct shape that is the only one that will really fit the blocks you want together in the way you want them to fit together.
The way that you want them to fit together. And imagine at the same time that the Legos are trying to break apart. They're of low quality.
Right.
And so if this takes a week or two, they're not gonna survive. You need the workers to sit there and make sure that things happen in a timely way. Once you can't put the tires on it until somebody's put the axle down. And if somebody comes in with the tires and tries to stick them on the car, well, they're there now, but we've got no axle.
They're going to fall off.
And that's what happens. That's how we end up with misfolded proteins.
Yeah. Right? Well, what you mentioned about putting the first Lego block down is a really good model for speciation too. Like when you look at earlier forms of life, like what the hell, the Cambrian or whatever, when animals were simpler. Once these pathways basically got, and the same with gene regulatory networks, once they get laid down, there's no going back. Basically, they have to go forward and become something else, and that's how we came to be. Yeah. And I don't know where we're going, but
polyploidy speciation is an amazing example of that, where the gene gets duplicated some even number of times, 8 or 16 or 32 or something, right? And as a result, you've got a new species, right? And so it can only mate with other polyploidy, polyploidy variants, right? And that's a new species, and that's a one-time. You can't go back on that. You now have 32 extra chromosomes. There's no returning to that unless there's some additional mutation. You now have to go forward with those additional 32 chromosomes.
Yeah. That's why you never see a dog give birth to a cow.
Right.
According to Kent Hovind.
Oceanus, you should come up on stage because your comments are totally on fire. You're adding, he's using another great analogy. I really like the assembly line analogy. He's also talking about the rubber band car analogy, about how like the rubber band car is the simplest version of a vehicle, and we're talking about the simplest version of life. And he's been adding some great points. So Oceanus, I commented the link in the chat. You're welcome to come up on stage and talk with us if you like. I love the commentary you're adding in the chat. If not, keep chatting it up. Great, we enjoy you. So we're talking. We've been talking a lot about protein synthesis and protein folding. Let's talk about some of the actual organisms, because we just got an answer kind of to what a gene's protein sequence and how it folds into its final shape is like, all kind of tied together. Let's talk about some of the actual shapes, some of the innovators that exist in nature. like our extremophile friends. Let's finally get to turning up the temperature like you were talking about, T.
I love extremophiles. They are what we would consider life under extreme conditions. Boiling water, right? Which we normally associate with dead stuff. The reason that you put your chicken in boiling water is to kill whatever's on, right? But extremophiles can overcome this by using different chemical bonds and different structures. So a great example is extremophiles of
we hear you.
Right? They don't denature at boiling temperatures. And acidophiles, they live in battery acid pH levels. And halophiles, which thrive in salt concentrations that would kill normal cells. The reason that they're able to do this is because they took a different chemical pathway, and they have chemical structures which are naturally resistant to things like denaturing at that temperature.
I would like to interject here. We took a different chemical pathway. Those were the original pathways.
Absolutely. Absolutely. Right? Yeah. And that's the fun thing about biology is like you learn like, you think a falcon, and an eagle and a parrot, and you wonder, which one is more related to the other. It's the falcon and the parrot, not the falcon and the eagle, right? They're actually, the descendants tree is more recent. And that's like, what? That's so unusual. These little things in biology that you learn just by studying the evidence, right?
Yeah. Yeah. So you were saying in your experiments with proteins and in your simulations with proteins that you could increase the heat in the simulation space and the protein would still find a way to fold. And that kind of fits the data of extremophiles existing, especially things like you call them superthermo extremophiles, which, wow, that one's a mouthful. But basically, it just means organisms that can survive really, really intense extreme heat, right?
Well, the most important thing that we learn is that life doesn't have to be the way that it is today. It can be different. It can happen through a number of different chemical pathways, and it's really 100% environment dependent. When you put those same chemicals in a different environment, you end up with different chemical pathways. And those chemical pathways, we don't necessarily recognize them as life presently. And that's why extremophiles are so interesting. They show us other chemical pathways that you wouldn't observe those if you were just looking around you in biology. So life is chemically flexible. It gave us confidence that when we use directed evolution to produce enzymes beyond their natural function, we'd see that nature, they've already done this in extreme environments, right? Nature's like step of the way. Nature is so ahead of the game. Like, if you look in the soil, there are solutions that humans are just completely ignorant of, right? Nature is like epic, better, cosmic brain, and we are dumb in that regard,
One of the things I like about extremophiles, and you were kind of touching on it there a little bit, is that they demonstrate the nature of evolutionary trade-offs. Like, yes, these are things that can survive an extreme environment. 200 degrees, no sweat,
Right.
But they're so ridiculously simple. In order to survive that, like, pretty much all they can do is basic response to stimuli. They are designed in a way that their chemistry allows them to be alive, but their version of life is way, way different from our version of being alive.
Right.
And that is a necessity. Otherwise, their own environment would destroy them.
Right, and that was the fun part in like running the simulation, is you can decide when the temperature gets turned up, right? You can let it go halfway through and then turn up the temperature later and watch the proteins fall apart. And like, organic crane, like origami cranes that are melting into pieces of paper, right? That's what it's like, right?
That's crazy.
Thermal cycling drives all kinds of reactions. It really does.
They stay rock solid. They continue They have extra hydrogen bonds, for example, right? They have different amino acid compositions. They have more rigid structures. They're like origami, but made with like construction paper and glue, right? Like that would be the like we have the cheapo folded versions. They have like the really military version. You know what I mean?
Yeah, that's
It was,
fascinating. You know,
it was originally,
sorry, go ahead, Ocean.
let's talk about the progress. Let me interject just for a moment. I'll keep this
Sure.
short. Let's talk about the progress of science. Originally, we thought that no life could exist near ocean vents because we knew for a fact that extreme heats would denature proteins.
Hmm.
Just the fried egg analogy. And since then, we've grown older and wiser in our science. I'm all done. That's my comment.
Yeah, no, that's totally true. And I think I'm old enough to remember some extremophile discoveries being a big deal in science precisely because they showed us that what was maybe not necessarily true. And of course, now we know it isn't, that partly and thanks to Dr. Arnold's work. And I think we can learn a lot about the origin of life and the very early stages of evolution by synthesizing these facts, by looking at extremophiles and looking at things like what Dr. Arnold and T were able to do, where they were able to propose a viable pathway by which a protein or an enzyme could evolve into another kind of enzyme. It's incredible. Especially one that can create other enzymes. That was what you said, right?
Yeah, the autocatalytic process of enzymes.
Wow.
Right. And what autocatalytic means is that the process of creating another enzyme results in the necessary parts to create another enzyme. Right. It's a process which is self-sustaining because it can keep going. Right. That's the auto part of the autocatalytic. And it's producing the catalysts in order to continue the process.
Yeah. Scott has a question for you, T. He wants to know if you've done simulations of various exoplanet environments or speculated about alien life. A little astrobiology question there for you.
Yeah, I mean, everything points at it's a walk. Evolution is a walk through random probability space. And planets are just directed points on that walk, right? Earth happens to have arrived at one solution, but there are others. We know it. We've seen it. They're out there. We just are going to be separated, and here's the important part, by not just great amounts of space, great amounts of time. And the reason for that is relativistic travel. Right? When you look up at the stars, you're not seeing the star as it is today or yesterday. You're seeing the star as it was billions of years ago. That's what separates us from other life is time, not space. Well, space-time, if you will, right? They're one in the same, and breaking one, you can't have one without the other, as it were. And so it's wrong to think about it in terms of how many light years away, unless you're thinking about how long it takes for light to travel, and then it makes sense. The Great Barrier is time, right?
Yeah, I have said before that this is a quixotic question because the very thing that makes it pretty much guaranteed statistically and logically that there's other life in the universe is also the same thing that makes it statistically impossible that we'll ever communicate with any of that other life. And that it's just how massive the universe is, that there's all this chemicals and energy out there and all of that empty, vast space that's not actually really empty as it turns out. But you know what I mean.
Yeah.
I would like
not a lot of hard
to
matter.
make a comment and back up to something that Austin alluded to earlier. So you'll see this with people that are anti theory of evolution, and that they'll look at, and this is one of the things that's really popular lately, is they'll look at this particular protein that lodges within a cell membrane that pretty much is used to be the axle for a flagellum to spin on for a bacteria or for a protist or whatever. And that they'll look at this and say, look, it came together in a ring structure, and that from nowhere. But the fact is it didn't come from nowhere. The ion control gates within a cell's membrane also has a ring structure, and it wouldn't take much of mutation in that to change the function of say a set of proteins that work together like that in that case. So you got our living things need these sodium and potassium gates all of the time, and we're constantly regulating these ions coming into and going out of cells. And that's pretty much what we think the flagellum, this particular protein complex, which is responsible for the function of cilia and flagellum, where that came from. So in nature, we're seeing, it's not like nature's just using it an empty toolbox, and starting from scratch every single time. And creationists would love you to think that that was the case, but they're being dishonest about it. We've got things hanging around. We've got structural proteins hanging around that could be reproduced for, or repurposed for other things. And it wouldn't take that much. I mean, we're not starting with a blank slate every single time, but they want you to think so. That's the end of my comment.
Yeah.
I'm actually so glad you made that comment, because when me and T were planning together to get together and do this talk, we had said we weren't going to spend much time starting over from the ground up like the creationists wanted us to.
Right.
The basics in this talk are protein evolution, enzyme. We're past evolution on this one. We're at the enzyme evolution level. But your comment was spot on, 100%. Totally agreed. They do want you to start over every time. They want you to build every single time you have an argument with them about evolution. They'll want you to prove all the same arguments you've had with them previously. And it's true that they think the scientific method has to start over from scratch every single time it tries to solve a question.
Right.
Yeah, basically.
True.
Scott wants to know, he's got some questions for you, T. I think you've got him fascinated. What are T Savo's thoughts on fine-tuning and anthropic arguments?
I'm not aware of any evidence of a method of tuning. What I do see, with regards to the universe, what I do see is a process by which life is constantly being tuned to a changing environment. So that suggests the opposite to me. That suggests that the environment is the thing that is just, chaotic. And life is the thing that is constantly tuning for a changing environment, right? And I think we have really good examples of that, right? A lot of good examples of, of adaptations, right? As far as, the anthropic is that the beautiful universe? Like it's just so complex. Like look at it. I'm not sure which one the anthropic is, or if we're just talking about another name for fine tuning. But I think that fine tuning is best captured by Douglas Adams' puddle argument, where you're looking at a puddle who has found itself in a hole that is so incredibly well designed for it that every aspect of it perfectly models the puddle itself. Every crook, every bit of space down at the bottom, every bump perfectly models the shape of the puddle itself, right? Therefore, the ground must be the thing that conforms to the shape of the puddle. And it does, and it keeps on thinking that to itself as it slowly evaporates into nothing. That the ground is the thing that was designed, not the puddle that's doing the conforming. I think very strongly that the right analogy is that life is like a puddle. It is the thing that wraps around that little nook and cranny and finds little crevices to occupy in terms of, environments that it can figure out a solution for, right? And extremophiles are just one more little nook and cranny that the puddle has creeped into.
That's a good analogy for consciousness too. Consciousness is just that process of constantly shaping to what's going on in your body and the world around you. And it's just sort of, and it's always relational. There's always a relation between the puddle and the whole, right? And it's never just one thing controlling another thing. It's always relational. But when you start thinking about, and we don't want to get into consciousness, but that is a really, really good way to think about consciousness, that we are constantly in this flux, adapting to what is going on around us. And everything is impinging on us. And so consciousness is very much in the body and the world around you, as well as in your brain. So anyway, something to think about.
I'd like to make another really valid point here. So creationists like to think that, okay, they want scientists to present a way that we can get from naturally occurring chemicals to life using like a chain kind of sequence. They want us to provide the exact chain step by step by step. And the number one thing they ignore all the way across the board in everything they say and do is parallelism. They want it to happen, like in a single place at a single time, where, a bunch of impossible miracles all happen in sequence in a chain. And if that hadn't happened, then we wouldn't be here. Mm-hmm. That's what they're trying to paint us as saying in that, but they'll ignore things like the parallelism, like okay, they'll reduce all of evolutionary theory down to the size of a thimble with a little bit of water and 2 chemicals in it. And I'd agree with them that life can't pop out of that. What they're ignoring are entire oceans, and that multiple reactions are occurring all over the place of varying kinds simultaneously. They don't want to look at things happening in parallel. They don't want to look at evolution as happening in parallel, that we might have a protocell over here and a protocell over there, and this one dies off and this one succeeds. They want to ignore that every single time. That's my comment.
Thank you for that. I've been harping on that forever. It's this idea that we can take a flask and pour some biochemicals into it and create life in a flask. Well, you would have to have quadrillions of different flasks all smashing into each other in a boiling hydrothermal vent in order to create anything, basically, for any of this to happen. So it's very important to think about how many microenvironments there were in the origin of life in parallel.
Over time, and with changing, chemical ecology on the planet, as the atmosphere changes, as things in the oceans start to use up more of the carbon dioxide, and the atmosphere becomes more oxygen based. Yeah, all kinds of changes have occurred on the planet. So development happened alongside those changes. And that is what the evidence tells us, as far as scientific consensus, and every scientist in a relevant field will tell you, like geology and biology. But you get a lot of people on the internet who say it's all hoax, it's all Masonic and satanic and evil. But we're having fun. We're having a good time.
Before we move on, I want to just respond to all of that, because I think that there is a really big misconception. It's common. It's not just a creationist thing, right? No. It's actually a very common thing that people think that evolution has anything to do with the origin of life.
Yeah.
It doesn't, unless we're talking about chemical evolution, because obviously we're talking about a time in which life didn't exist yet. So we couldn't possibly be talking about biological evolution, because that's how populations of genetic organisms evolve over time. That's not the origin of populations of genetic organisms. And so that's one of those things. They go, well, evolution doesn't explain the origin of life. Well, that's correct. Abiogenesis is the research program regarding the origin of life. Evolution is the research program regarding how populations of genetic organisms accumulate change over successive generations. They're 2 different research programs. There's a third research program. You might have heard of it. Artificial life, also known as biomimicry, the attempt to create life in the laboratory. This is a yet third endeavor, a yet third discipline that is in many ways removed from abiogenesis and evolution because they're not doing the same thing that occurred on prebiotic Earth.
Right.
On prebiotic Earth, the process that occurred took millions of years.
Mm-hmm.
We just
Yeah, it's not what they're it's not what they're trying to do. They're not trying to create life
right?
in a test tube.
Right. So
Yeah.
systems chemistry, you start off in basic chem, and then you work up to biochem, which is the application of biochem of chemistry as applied to biological life. Okay. Then you get somewhere in between that is synthetic chemistry, right? The process of making chemicals. Cool, very cool stuff, right? Then beyond that is systems chemistry. This is the application of chemistry in a changing environment. Period. Right? And then beyond that, we get to abiogenesis, which is a specific field of research within systems chemistry.
Yeah.
Within synthetic chemistry.
And it's basically the fact that evolution is already an extremely well supported theory and model that's got just an overwhelming glut of data that supports it.
Right. We were
Abiogenesis
right?
and biomimicry, these are just fields that could strengthen evolution even more if they are successful. If they both completely fail, it doesn't make evolution any less valid. But if they do both succeed and find new areas and are robust and have testable, it makes evolution even stronger because it shows where the common ancestors could have come from for the evolutionary model.
It all gives us a better understanding of the chemistry.
Yeah.
Because at the base level is chemistry.
Yeah.
And then we have different applications of chemistry going up to, to biomimicry and abiogenesis and biological evolution. Okay? And then there's stellar evolution, right? How do the heavier elements form in stars? That's stellar evolution, right? How do planets form? That's planetary evolution. How do solar systems form? That's solar evolution, right?
Yeah.
And so all of these are just different research programs, right? And creationists so often confuse one for the other. They go, hey, abiogenesis hasn't created life in the laboratory yet, and it never will. That's artificial life. That's down the hall on the left.
Yeah, right. Right. So, are you going to want to take a break at all between this? Should we give the class a 3-minute break, or should we just keep trucking?
Want to just go offline for just 1 minute?
Yeah, let's give the class a little 3-minute break here, and we'll be right back.
Cool. Sounds good.
Right. I'm back. Just needed to stretch out a little bit. I've been sitting in ape computer posture for a good solid week straight with school and work and all that stuff. I had a lot of statistics assignments to get through yesterday. I ended up making like 35 different Excel worksheets to complete them all.
Oh, gosh.
Yeah, it was a lot, but it was fun. So let's pick back up off with the Extremophiles, and we can almost kind of synopsize the first half of what we were talking about there a little bit with this question. Could you give us an example of an enzyme from an extremophile and explain what makes it so special? Like in the instance of the superthermophiles, do we know which enzymes those are that
Back
don't
polymerase.
denature at those high temperatures?
Yeah,
Tachypolymerase, you said it was?
Yeah,
Yes.
that's a great example. And that's one of the cool examples because of what happens when you raise the temperature. When you raise the temperature, we could watch the proteins fall apart and the enzymes just unfold. And this particular enzyme, it just stays rock solid, right? And that's what makes them really special. It's their particular 3D shape, right? What's really cool about this understanding that we gained, it's not the chemicals themselves. They're all made up of the same 20 amino acids, right? It's the way in which the proteins fold. It's the chemical pathways that the enzymes take in order to get there, right? That's what makes the difference. That's the differentiator. And the differentiate, a lot of the times the differentiator on that chemical pathway is just the temperature alone. The temperature alone,
Right. Yeah.
changed by a few degrees almost completely cuts off entire important chemical pathways.
I'd like to interject here for a moment. So
Yeah, go ahead.
For the benefit of our audience. So with amino acids, basically we have an amine group and a carboxyl group, the acid portion, and that's why we call them amino acids. And we also have an R group to those structures, and that can include a number of other functional groups to them. And I'll try to make this brief and kind of plain, but these functional groups, they rely often on hydrogen bonding and other things in order to form, structures and that. And some of these proteins are in fact self-folding. They don't require anything because the energetics of the sequence contribute to stability simply because of the nature of the morphology, the geometry of the amino acids are more conducive to structural change. So we can't really speak of these things like it's
Yeah.
monolithic in that when we change the order and the sequence of the amino acids, sometimes we arrive at structures that are that will through energetics form their own shapes and stay there because it's energetically favorable for them to stay there. That's my comment.
Yeah. I'd say that, the thing that I'd say is everything's trying to become iron. That's the critical understanding about molecular geometry, is everything's trying to become iron because iron is the most efficient configuration of molecules where you can pack the most in and get the closest to keep them all there in that configuration, right? Any more, and you've got some sort of imbalance between stability, right? And any less, and you've got more a potential to add more in, right? So any more, and you'd have a lower energy state that would be required to break them free. Any less, and you could simply add more and get a more efficient configuration. The universe is trying to create iron, right? That's just the nature of chemicals falling into lower energy states.
Yeah, right. The second one I agree with. I don't know if I agree with the universe is trying to become iron.
That's the
yeah, right. Yeah, no, I get it. No, how exactly do you phrase it again? It's trying to evolve into a lower energy state? What's the exact wording? Sorry.
Chemicals, they just fall into lower energy states. But in doing
Chemicals
so,
naturally evolve towards
more
lower
complex,
chemistry states.
yeah, they create more complex macromolecules, right?
Yeah.
And that's the thing, is it isn't, and this is the really critical part, right? It's not the number of chemicals, it's the way in which they bond that really makes a difference, right? And so the final folded protein structure has everything to do with whether or not these extreme temperatures can shake it apart in boiling water, whether or not it can denature, right? It's all the same chemicals, it's different chemical foldings.
I'd like to introduce for a moment.
There are chemicals and there are parts, right? And the parts are made of chemicals, and the parts are things like the four main biomolecules, our proteins, our nucleotides, our lipids, and our carbohydrates. And those are all made of like 6 main chemicals: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfides. And if you have energy into that system over time, it evolves. It's like shocker.
And for chemical stability, I'd like to introduce my friend sulfur.
Mm-hmm.
Sulfur makes very, very strong bonds.
Mm-hmm.
I mean, disulfide bonds are powerhouses.
Incredibly.
And, and as soon as you have
curly.
those in amino acids and things of that, those things are stable. They are hard to tear apart, in that they contribute more to like stronger hydrogen bonds and other things that would prevent the protein from denaturing.
They can curl your hair.
Yeah.
Right.
So
what is the other?
that's actually how your hair curls, is with sulfide.
Arsenic is a really good one, because this bonds in a lot of the same places that carbon. Well, it bonds the same way carbon does. Right?
Yeah,
that's a problem. Yeah,
replace carbon with arsenic. A lot of these chemical reactions, and still where you're trying to go, right? So I mean, there's a lot of flexibility in the chemical world that's really unexplored, you know.
Yeah.
And if we back up quite a few pages and we look at an anoxic environment, oxygen is extremely reactive. It would be absolutely toxic to the formation of life in abiogenesis. But we're not looking at an oxygenated atmosphere. We're looking at enormous amounts of methane. We're looking at enormous amounts of other things in that, and we're not looking at an oxygenated atmosphere, which didn't come until later.
Yeah.
And in the field of abiogenesis, and that experimenters have to make sure that there's no oxygen there, because oxygen is so reactive and such a scavenger. So that's my comment.
Yeah, it is part of the great solvent, right? And that's the thing about when they're trying to figure out, they're seeing all these anaerobic life forms, and they're going, oh shit, life form without oxygen. Here's the proof: we have anaerobic life forms before we have aerobic life forms, right? That's fascinating work right there. That's the type of things that abiogenesis researchers study. They study what actually occurred. They don't try and they try and replicate the processes in order to demonstrate this is what actually occurred. But the research program is about what occurred. The research program of artificial life is about what we can do moving forward. Certainly, there's learning that's lots of overlap. There's if you draw the big Venn diagram, there's a big part of overlap, but the ultimate goals are different. One of these is to explain what happened on planet Earth. One of these is to make it happen again today. It's a different process, and it's not going to take millions of years like it did on prebiotic Earth, right?
So this is one of the areas of your expertise where it's like I can see why this guy sometimes has to deal with creationists online, because Dr. Arnold She won her prize specifically for something that is sometimes called directed evolution, right? Which, if you're a creationist, intelligent design type, you're like, oh, directed evolution, oh, intelligent design, friggin' game over, evolutionists, we got you. The evolutionists admitted they need intelligent design. Which,
And I want to interject my pet peeve. So my background, so the other panel members might not know, is in molecular biology. So, and they want to pull out the watchmaker and how like living cells function as a machine. And it's like the hell it does. The way a living cell functions is throwing spaghetti at the wall and seeing what sticks. I mean, just in replicating DNA, it's error prone. Everything and every step along the way is error prone. It's inefficient, it's sloppy, it's error prone, and that's what makes it great. That's what makes it work. It's
100 mutations per generation, right?
it's using the shotgun method the whole step of the way. They'd like you to think that it's strict and structured like the components of a watch, where every little gear is on a tight little hub, and it's not like that. We have Brownian motion carrying most of it.
It may be like that if it's working well. If it's working really, really well, it may be more ordered and normal. But the thing is, 99% of what has existed has ended up in the scrap bin. And even still, with all of that refinement, there's still all this messed up design and.
The philosopher Daniel Nicholson basically pushes back on that cell as a machine sort of thing, and he does a really good job. One of the examples he used, that the microtubules, that little walker that they always show walking on microtubules in animation, carrying a ball, that sort of thing. Yeah. Well, apparently that may not be true. It may be something entirely weirder than that. And of course, at that level, we have trouble visualizing what atoms and molecules are doing, but it's more of a saltation type movement and in these chemicals, and it wouldn't look like that if you could shrink down and see the molecules, even though it's a lovely animation. But anyway, things like that are misleading about the cell, about how cell. And the other thing is the cells are really packed with proteins. I mean, it's really like thick gel in there when you get down to that level, and very stochastic. It's not what they think.
The animations, much like charts and drawings, they're just visual representations of a data. They're visual representations of a model, and sometimes they're wrong and they end up needing to be refined. Other times they need more context added to them to be more accurate. But a lot of times they can't be useful, even if they are kind of wrong, like sometimes.
Yeah.
The other issue with the animations is they're slowed down so that somebody can kind of grasp what's going on. We're talking about really minute distances that a protein has to move, and we're talking about reactions occurring in very, very sub-millisecond time intervals and that. And so they look at it and just like, oh, well, that's horseshit. Look at, how this is going. And then we're going to ignore parallelism all over again. We've got other stuff going on that's not shown in the animation that's driving that.
Yeah, I'm sorry if I got a little animated there. Creationists, get my collar up a little if you hadn't noticed. No, can you explain what directed evolution is?
Yeah,
like what it actually is, so that we can clear that up.
Yeah, we can really get this on the record, right? Directed evolution is when you apply statistical analysis to the process of evolution. Evolution is the process that we observe occurring when a population passes on its traits to the next generation and accumulates change through doing so. Okay, so this applies to chemicals, in that chemicals can pass on their traits like through enzymes, right? So when an enzyme, evolves into something new, but it keeps its old old ability to replicate, to synthesize more enzymes through an autocatalytic process. That's an example of chemical evolution. Right? When populations of organisms gain lactose tolerance, right? They're able to drink milk again. That's an example of evolution. That's a change in the population at the genetic level. Right? And so directed evolution is applying statistical analysis to this observed phenomenon. This is something we observe, and then we apply our analysis to it, right? And then computational biology is the application of directed evolution to computer science. What we're going to do is we're going to take all we know about computer science. We're going to say, how can we do statistical analysis of evolution and try and predict what is going to happen at the chemical level, at the cellular level, at the population level, whatever it is that we're going to evolve, right? Doesn't matter. That's directed evolution, because what we're doing is we're trying to do some sort of statistical analysis against what's going to happen to predict the actual outcome. And then we go and we, take those chemicals to the lab. We take those observations to the anthropologists and say, what does your data tell us, right? We're trying to make good predictions. We're trying to build models, and these models are based on actual observances. They're based on facts. They're based on data that we go and we collect in the real world. We try and predict, where that data is headed, and then we see if
So directed evolution isn't even like an actual phenomena. Like it's a phenomena, but it happens on statistical analysis tables. Like
right.
when creationists take the term directed evolution and run with it, that's very ironic to me. That's funny.
You're going, no. We're studying a naturally occurring phenomenon.
Right. Yeah.
We're applying statistical analysis to what we see happening. Literally. That's directed evolution. Right?
Yeah. Okay. So what is the scientific community's reaction been to everything with directed evolution and Dr. Arnold's enzymes and the possibilities of protein synthesizing and folding technology in medicines in the future and stuff like that?
It's been really humbling to watch what's happened since 2018 or 2015 when we were working on this, right? And then 3 years later she wins the award, right? It's gone in directions that I never ever could have imagined. We laid the ground for computational frameworks, but the research has taken on a completely different direction that makes our work look very quaint. They're now using directed evolution from everything to biofuels and pharmaceuticals, and that's been amazing to watch, and it's exploded in ways that I never ever would predicted. I think it's primed to go exponential at this point. The discoveries, I think, have just begun. The discoveries of the next 10 years as a result of the work in directed evolution will outpace the results, the actual cures of the past 100 years in terms of magnitude. We are talking about new types of drugs, new forms of therapy that don't look like drugs anymore because they're just fundamentally different. We are on the cusp of better understanding our biology, and that's because these tools have exploded in potential. We are literally, in the moment of acceleration, in the big ramp in which we've been going along, we are in that moment of acceleration right before we go hockey stick, right? We're down here, and we're about to go here, right?
As long as we keep the funding.
Done, right?
Oh my goodness, yeah. And
as long as we keep the funding.
I wonder if there's like some civilizational critical mass where if you haven't evolved enough emotionally and socioculturally, psychologically, biologically, like if
Yeah,
you get to the level where you have that level of understanding, you're just going to destroy yourself and wink out. And that's maybe the reason for cosmic silence along with cosmic distance.
I'm
But
way more optimistic than
yeah,
that.
I think that
yeah,
the scare that AI is going to replace humans is a bit silly. I don't think that's
yeah,
really going to happen at all. I think that humans who use AI are going to replace humans. That's what I
yeah,
think is going to happen.
augment. Yeah,
And I am so serious about that, and I've got the data to prove it. You know what I'm saying? Is
Well,
people
20 years from now, it'll be like humans using cars replacing walkers.
as a coder
yeah.
has coded
The-
all of his life, I no longer code, and I get more code written than I've ever gotten written in my entire.
Exactly. Yeah, I use AI about 4 hours a day for genome research and anything I got to code. It's like I'm not going to sit down and puzzle out an algorithm, and I'm just going to get it done, get the tool done.
Yeah.
It's kind of scary for programmers, though. But
Yeah.
the thing is, you definitely have to curate that code because it can really screw up. I mean,
you still have to know how to code, right?
yeah. Me and my
know how to code using AI to code who will replace human coders who don't use
yeah.
AI to code, right? It's just
Me and my son. Me and my son defined it as working with a absolutely genius novice programmer. Basically, you're working with a novice, so you have to. The senior programmer has to bring them along.
A junior coder who can code at 10 times the rate you can.
Right.
That if the senior coder can give him very, very, very specific instructions, this will work out fine. I promise. Yeah. Right?
Yeah.
So you used your skills in computer science and biology to contribute to Dr. Arnold's research, and now things are blooming from it in ways it's kind of almost difficult to list how much potential it has. That must feel incredible. But how do you think your skills specifically contributed to their research? Like,
I mean, it's very specifically in how we model their code in terms of a GPU shader. GPU shaders are just a little bit more low level. You have to, at the beginning of the code.
Can I 1 second? You've said shader like 4 times, and I think I kind of understand what that is. But can you give me a more specific definition?
Okay, so
shader.
Typically a CPU.
Is that like Blender or something like that, or
it's a little bit different. Typically, a CPU is running one piece of code, right? And that's like Photoshop or Word or Chrome or whatever. That's a piece of code, and it runs it, right? And other pieces of code can run on the computer, but they have to share the CPU. Now, in order to get around that, what manufacturers do is they pack multiple CPUs onto the chip. So the typical computer can have anywhere from 16 to 32, upwards of 6428 cores. Right? Right. And what this does is this helps with parallelization. Right. There's a difference between concurrency. Concurrency means that both Chrome and Word and Photoshop are running at the same time. That's concurrency. Okay. So, but that means that one has to go, and then the other has to go, and then the other has to go on one CPU. So what they do is they add more CPUs, and what that allows them to do is that allows them to run in parallel. Think lanes in a highway, right? You can have a really fast car, but if you only got one lane, a bunch of traffic on it, you can't go anywhere. You need more lanes for more cars to go at the same time. That's parallelism.
That's okay. Yeah.
So concurrency is, multiple things happening. Parallelism is multiple things happening at the same time, right? Okay, so GPUs are a little bit different. Instead of having 1 or 2 or 4 or 16 or 32, they have like 16,000 compute cores, okay? But the compute cores are more simple. They can't do all the same things that a GPU can do, okay? What they can do is they can operate on a big chunk of data, okay? And so what you can do is imagine that you can take that one program and you can run it across every single piece of data. I'm going to run it on this piece of data. I'm going to run it on this piece of data. I'm going to run it on this piece of data over and over and over. Except instead of having to do this one at a time on a CPU, I can do all 16,000 of them just like that, chunk or bang.
And so in this case, the data we're talking about are like possible protein conformations.
They're literal combinations of proteins and the activation states between them in terms of probability.
That's so freaking cool.
Is we want to model how those activation states occur probabilistically and then modify the underlying data, the big chunk of data, right? But we want to do that one piece of data in the vector at a time, massively in parallel, right? That's the trick.
I love parallelism.
Because the way that they were doing it is they were doing it, we can do one at a time. We can scale it up to like 32 at a time, 64 at a time on a machine, right? My trick was going, no, 16,000.
16,000, yeah.
Right?
Yeah.
It's a bit faster.
Yeah.
So can you explain more about shaders?
Right. And so the whole thing about shaders is you take your code, you compile it for the special chip called a GPU that runs on a computer, runs in parallel to the CPU. You take the code, you give it to the GPU, you give the data to the GPU, and then you go chunk, and it runs it across 16,000 pieces of data all at once. And you do it again and again and again and again, and you do it just as fast as you can in order to get the data.
So the compiler decides how to break it into parallel processes?
Because each little cell is a parallel process. You have literally 16,000 compute units running in parallel, and each compute unit gets exactly the same code.
Yeah.
So a shader functions like an algorithm that you're handing off to the GPU,
right?
And telling it to run this algorithm on all of the compute units.
Right, but you're only going to run one algorithm, and you're going to run it 16,000 times.
Right.
In a cycle, in one cycle, and it's produce 16,000 new values. Right. So, it's gonna modify the underlying data, and then what you can do is you can read that data back off of the GPU into the CPU, which is what they do for games. Like, for example, imagine that you have your world state, right, and then you need some physics to happen. And so you need to modify, you've got, your force times acceleration, and then you've got some moment of inertia, and you need to modify your vector to end up with a new world state. Chunk. You want to do it against all of the world state all at once in a single cycle. That's what the GPU does, right?
In the old days, we had all these trying to do parallel processing. We had forks and semaphores and meetups and all this crazy stuff, but that's all sort of automated with this GPU compiler.
You don't have any of those.
Okay.
You don't have mutexes. You don't have semaphores. You don't have data sharing. You don't have DMA. You don't have anything. All you have is the data coming in and the data going out.
Okay.
And then that data going out replaces the data coming in for the next cycle.
Yeah, I think chunk is my new favorite onomatopoeia.
That's great for modeling dynamical systems, and it's pretty cool.
So eventually,
very low level, all you get is data going in, data going out. You have no I/O whatsoever, right?
Eventually, we're going to have to prepare for AI functioning in parallel. So we're going to have different specialized AI, chips and algorithms, and learning models and that working in conjunction with each other.
Yeah.
You know, for a special, we might have a protein folding AI.
Agents.
We might have a, you know, another one that deals with the function of the protein once it's been folded, AI.
Yeah. Agents are the framework by which AI collaborates with other AI. And it's amazing what's happening in agent land.
I want to do another pet peeve. My other pet peeve
Sure.
is the analogy of DNA to computer code. DNA has the sloppiest syntax
Yes.
you can imagine. I mean, sometimes, I mean, you'll have a mutation. They want you to believe that all mutations are immediately deadly.
Deleterious,
E-
yeah.
yeah. Even though there's a number of instances in the way the DNA is transcribed in that, just like you get a change of one nucleotide, and it will still accept the same amino acid. It's loosey goosey. It's
Yeah.
very loosey goosey.
That's
my point.
All analogies break down at some point. I think the code analogy happens to break down especially fast, and the assembly line analogy is just a much better analogy because
For sure.
like
Way
blueprints,
better.
workers, managers, you know, individual parts
Yeah.
which get assembled. That's not like code. That's more like an assembly line than code, right?
Yeah.
So I think have we said everything we want to say about the state of the field of protein engineering since your research, or was there anything else specific you wanted to talk about that before we move on to the future of technology and life and science and where all this is headed?
Oh, and I mean, the future. I'd love to talk about the future.
All right, let's jump onto the future then.
Well, I think the old ways of doing things are going to disappear. I think you're going to see designer drugs that are tailored to the person rather than are tailored to the masses. And that's going to be the fundamental shift.
We are already kind of seeing that, right? Like I think a good example is the fact that we don't have to use pig insulin on people anymore. We can use human insulin on them because we can turn a yeast into a little useful biochemical factory, which makes their freaking the assembly line analogy holds up yet again.
I think that 3D synthesis, I mean,
Yeah.
you 3D printer. Well, I think 3D synthesis, that's the new wave, right? You know,
Yeah.
it's not going to be, you know, a pill which comes off the assembly line. It's going to be a pill which is 3D synthesized for you. You know what I'm saying? And this, you know, and that's the reason for that is because we can just go ahead and design a protein specific for your body.
I'm glad you said this because when you were talking earlier about we're going to have medicine that doesn't even look like medicine, I was like, how am I even quantifying? How am I conceptualizing? That is, I get now kind of what you're talking about.
You
Yeah,
want to go?
like
You want to go the extreme?
you get an Austin Sims protein if Austin Sims gets sick instead of, you know, just some generic compound,
Right.
some analgesic or something.
Right. So you want to think about the right way to think about it is you will no longer take the cure. You will instead take the thing which prompts your body to grow the cure. That's the right
wild.
Right? Okay. Now, if you want to go the extreme, think about how that might, I don't know, 50, 100, 200 years, how that might evolve, right? Is you no longer buy a cell phone, you purchase the modem trait, pop the pill, and overnight grow the antenna. Think about it.
I'm all for it if it can give me armor, if it can give me fangs, claws, wings, or if it can give me 4 to 6 arms like Goro from Mortal Kombat or Machamp from Pokemon. I'm on board with all of that. I've said this many times.
That's the right way to think about it, right? It is and the reason that I bring up the logical extreme is because it prompts a path there, right? How do we get to that? How do we get to growing a cell phone in your brain, such that when I want to answer the phone, I don't have to pick up my device any longer.
Yeah.
How do I grow a modem? How do I grow an antenna? What is the pathway there? Well, it starts with basic protein synthesis.
Dude, I'm sure Christians are like shitting their pants if they're watching this right now, too. They're like, oh my God, he wants the Satans implanted in his head.
It's a purposefully
What a demonic man.
It's a purposefully extreme example to prompt a layer of thinking, right?
No, but I love it, and I think it is absolutely a great example because if it were real, 100%, I know people who'd be lining up the cell phone,
grow the latest cell phone,
100%.
Yeah.
Well, can you imagine if the wealthy got a hold of a youth pill?
Yeah.
Now they could take a pill and they become youthful again, and they achieve virtual immortality.
Yeah,
because
we're really we're in like sci-fi. That's basically the plot of the movie In Time with Justin Timberlake, and it's a great movie if you haven't seen it.
For a girlfriend.
Yeah.
Right. I mean, that was probably the easiest, the best line in the whole movie. Right. Time for a girlfriend.
Yeah.
What was he saying? Right. He was literally saying he doesn't have the money for the girlfriend, but in the movie, money is time.
Yeah.
Right. I mean, it was just a brilliant commentary. Right.
It was a great movie, and it was very deep. It was very original too. Yeah, it was one of those rare. Listen, you don't get a lot of original movies nowadays. I don't think.
Totally.
It's my opinion, but that one was a good original one.
Tear down the eye when the mother died. Just saying.
Yeah, for sure. Yeah. So what are some of the most exciting potential applications of directed evolution and protein engineering that we could see in the next 5 to you've mentioned a couple. Are there any other that you haven't talked about?
Right off the bat, a cure for cancer.
Cure for cancer. Yeah, right. Yeah. We touched on that. Yeah.
Start there.
Yeah.
We've got the money to put into that type of research, right? We've got the funding and the infrastructure in place. We've got, St. Jude's Hospital, for example, one of the most amazing examples of a humanitarian establishment, right? Parents there, when their sick kids go there to get treatment, the parents never receive a bill. I don't know if you knew that.
Yeah.
Right. But it's like there's an opportunity, right, to actually help children grow up to be adults. You want to talk about a change, right? We could change the death rate of people under the age of 18, right? Global warming, that's a trickier problem, but we could do some engineering. I don't know, let's talk about at the cow level or the grass level, right? And I think that that's so much bigger than people understand. I think our understanding of cows is ridiculously behind that of humans. We have to play catch up there, right? There's a lot of learning about the microbiomes of cattle guts, for example. We could do a lot of engineering there. Yeah. We could design enzymes for carbon capture from the atmosphere. There you go, right? Yeah. We could create better plant proteins to reduce the need for livestock. When you're dealing with billions of livestock animals or vast agricultural systems, the computational and engineering challenges are simply enormous. They are of a scale that we need to tackle. And it's the type of thing that we can't tackle overnight. And it's the type of thing that we're not going to get right the first time. So we need to be iterative and we need to be proactive. So there's lots of opportunities there to really affect the course of humanity, if you will.
I propose.
So part of the reason I study biology, it's fun and cool to think about getting wings and armor and fangs and claws and stuff. That's fun and I love that. But part of the reason I study it is because it is applicable to problems that are facing the planet. People are getting sick. They're getting ill. They're getting disease and wounds. They're addicted to all kinds of chemicals. They're getting bad food that's poisoning them, and they're developing addictive cycles with that too. And nobody's getting enough mental health care. And all of this stuff is biology's core to all of it. Food insecurity, agriculture, getting safe, healthy, clean food. And it is because of that that I love biology so much. And why the freaking creationists tick me off so much is because we're just trying to solve problems here, and you guys are not getting in the boat and rowing.
I'm writing a book. Well, I'm working on kind of a novel. It'll never get done in that. So basically, all the scientists group together and form their own country because they have to, and address all these problems without all these societal pitfalls that we keep running into. And it's not just creationists. We got people against transgenic organisms and genetically modified organisms that have no idea what the hell they are even talking about, while they're using wheat that used to be grass and eating wheat that used to be grass and everything else. They don't like the scientists. They don't want to have science to be enabled in any way whatsoever. As soon as they hear the word science, as soon as they hear scientific terms, they're going to go straight to their favorite fairy tale and talk about the destruction of society, and we're getting demonized. We need our own country.
So,
yeah.
Oceanos, I love that you brought that up, because the point that I was getting lost in when I was talking earlier is, like, think about if we could use directed evolution, if we could use gene therapy and gene manipulation to make a species of grass that's semi-edible and spread it all around the planet so that everyone's lawn is now suddenly a food source too. Now you don't have to worry about mowing your lawn. Let that sucker grow. It's dinner for you if you want it to be. I don't know what the actual genetic potential for something like that is, but it could be done, because technically corn, Zea mays, is in the same family, Poaceae, as this grass that grows in your lawn. Right. So
we should
like
dump
that.
all of that. We should dump that line entirely and go with quinoa. Now, quinoa, quinoa is going to give you a lot of those essential amino acids and all that protein, along with the carbohydrates and the fiber and that. But we're stuck on these older foods and that. And quinoa will grow, as far north as Canada. It'll grow in extreme environments. It'll grow in salt-rich environments. It's really, really hardy. So let's get away from grass.
No, and talking about like being stuck on old foods, right? Is anybody eating protein cricket yet? Why not? It's the obvious choice when it comes to actually farming protein. It's cheaper, it's more effective, it doesn't pollute the environment like cows do. I mean, there's so many good ways to engineer new solutions for our environment. Right? There are so many opportunities here.
That one's got cultural things to overcome. Some people will have no problem with eating that. Other people will be like, gross, yeah.
Right, and that's okay. But here's the thing: all it takes is one generation.
Yeah.
Okay. All it takes is the 18-year-olds of today not buying a car in order to start working at their minimum wage job at McDonald's. Instead, they take Uber. And then they continue to take Uber as they climb the corporate ladder. And then in 10 years, they're a manager. And in 20 years, they're literally an executive. Okay? This kid now thinks differently. He's in an executive position. He's lobbying for laws. He's never owned a car before. How do you think that changes the mindset regarding gig workers?
Yeah, it probably does.
One generation. It only takes the 18-year-olds of today talking about skibbity dog water to become the policy maker of tomorrow, and they've never owned a car. I'm dead serious, right?
No,
Thinking about
I
that,
know you are, but
you're missing the
skippity
bus.
dog water kind of broke me. Skippity dog. Is that something they say now?
Yeah,
I know the skibbity part, but why dog water?
I don't know why dog water. I don't know, but the answer to the assignment. That's another thing they say is the answer to the assignment.
Oh my gosh. Okay. So I know a bunch of people are watching just because they want to hear us address this topic, but I'm not sure if we want it to be the last one we bring up. I guess it depends on how much we talk about it. And I'm going to say 2 letters, and I bet just because I told you I'm going to say 2 letters, you already know what those letters are. AI, artificial intelligence. We need to talk about it. Some people hate AI. Some people are terrified of AI.
Mhm.
Other people love AI and are obsessed with AI.
Yeah.
I actually work in a field that involves a lot of AI studies. T, I think that is somewhat true about you too. Am I correct? Yeah.
Sure, it is. Yeah. Yeah, you
Well,
know who,
just give us some of your general thoughts, and then let's ask a specific question too. What do you think the technologies like AI and machine learning will be like hundreds, thousands of years from now, assuming humans survive and are still making them?
well, I think we've already caught a glimpse of it. As far as I'm concerned, I got blessed with the Harry Potter magic wand. Quite literally. I'm not being facetious, I'm not being hyperbolic here. When AI gained the ability to start coding around Claude 3.5, that was a game changer for my productivity code-wise. Instead of being trapped with, I had a motorcycle accident almost 4 years ago and lost the use of my right hand. So instead of being trapped with one hand behind a keyboard, I am now writing code at ridiculous rates. Those rates are only going to accelerate. They're going to accelerate, and here's the important part, beyond my capacity to utilize them effectively. AI will start writing code faster than I can direct it on things that I needed to write code about. That's how fast AI will be in the future, right? It will. Today, you ask it to, design a website, and it does a mediocre job. In 100 years, you ask it to design an entire enterprise system, and it will materialize it in seconds, fully formed, with unit tests, bug-free, the whole 9 yards. Exactly.
Oh,
It is what we are seeing today accelerated. Nothing magical about it. It's the simple progression of what we already are getting right now. And it's the magic wand for creators. People who are scared of AI are the same people who were working on movies with a paintbrush when Photoshop started getting serious about digital photo editing. They were scared shitless of Photoshop. They had said, I am pissed at this whole digital effects thing. Computer generated graphics, that's a fad. That's what they said.
Yeah.
They said that's not
Yeah. You see,
right. That's what they
you
said.
see,
They said I hate this. This stuff this isn't real. I'm hearing those same things about AI, and I say let the
you
haters.
see,
Right.
you see that picture that I generated with AI yesterday for a thumbnail. I wanted something for. All I asked it is to give me a cartoon of an orphan gene that's living on the streets and is really sad. And it came up, and it thought up no homologs, and it put that
Hilarious,
wonderful,
right?
that is hilarious.
and it put that little DNA overcoat on it. It's just fucking amazing, and I didn't tell it to do any of that stuff. It came up with that shit. So,
We have
I mean,
trained
isn't that a
AI.
great orphan gene? Huh?
Yeah, it's
We have
phenomenal.
trained AI on country western music, and country western music, while not my personal brand of the thing I want to listen to, is hilarious. It is
Yeah.
consistently funny. And as a result, when you ask us an AI to give you a country western song, it gives you something that is genuinely Weird Al worthy. It is like, this could be on the comedy charts today.
There's
so funny.
I've seen YouTube content creators actually use that to their advantage. Like I follow some flat Earth debunker guys, and they make hilarious comedy country songs about flat earthers, like Austin Whitsitt and
So we already
Nathan Oakley.
We already see streaming music that is produced right there in the moment for your ears alone, and you'll never heard by anybody again. And anytime anybody else wants to listen to that stream, it's a completely new song, right? Generated for their ears alone. And I'm saying it's just the natural progression of that. Now take that methodology and apply it to games. I want to play a game that's Star Trek themed, except Kirk is an ocelot, right? You know, and Spock is a weasel, right? And Uhura is, I don't know, a skunk or something, right? Okay, and then that's the game. And AI 100 years from now, today, AI is going to go, okay, here we go, and you're going to laugh at what it produces. Yeah. 100 years from now, you're just going to dial it up, and you're going to play that game, right? And it's going to be exactly what you asked for. And it's going to do everything that you asked for it, and it's going to be custom to you. You want to watch a movie in which, you know, the Marvel and DC universe work together, no problem. Just like that. In fact, that never existed until right now when I typed it into my AI 100 years from now, and it created that movie for me. Right? That's what we're going to see. It's going to be a natural progression of that. And you've seen the progression. You've seen the art go from cartoony to lifelike, to photorealistic. You've seen the videos go from soundless to having people talking in them. And looking almost, you know, they started out here climbing into that uncanny valley. They're now climbing out of that uncanny valley, where you can no longer quite tell if it's AI anymore. And boy, they're going to plateau at that moment, that you know, that vision of enlightenment, where it looks identical to what you expect it to look like.
But we always end up in these uncanny valleys where art imitates life.
Yeah.
I've been telling people for a while now that if they have that super high-tech, expensive $10,000 AI, they should use it to make Donald Trump tell the truth.
Right.
Oh yeah.
I love if you have the evil technology, use it for some good.
So if anybody wants a really funny country song, not AI generated, "The Hand of the Almighty" by John R. Butler. Have you ever heard of it?
Yes.
I always play it for my Christian relatives, and they're like, "Oh God, he's playing a religious song," and then it winds up. It's just awesome to watch their faces.
Yeah.
It's cool.
Anyway. Yeah, can we take a quick second from the super. I'm loving the scientific conversation, but Captive Desk, aka our friend Dave, just gave us great news that his most recent check of his medical problem cleared him, and he's headed home, and he's feeling good, and we're all really happy for you, Dave. In fact, I think it deserves a standing applause, ovation, or at least a round of applause for Dave. Hell yeah.
Hell yeah.
Let's get together and do a Vulcan mind meld for Captive Desk. No.
That's an example of cancer, I believe, being cured. They're getting a little better at it.
Yeah.
I had kidney cancer 3 years ago, and I was going to get treatment here in the Twin Cities, and I ended up going to the Mayo Clinic, and they just kicked that cancer's ass. It was awesome. I think I would have died if it hadn't been for going down to the Mayo. You get the right doctors, you'd be okay.
Oh, but you could have had faith healing and you know.
Oh yeah, I could have prayed it away.
Yeah,
right?
yeah. Some pots and pears.
Yeah.
So do you think AI is going to help us solve more problems than it's going to create? Like, Is AI going to help
Hopefully.
us solve climate issues, or is it going to create more climate issues? Because we currently
solve
it
them.
uses a lot of water, right? It uses a lot of resources.
It's going to solve them, and the reason it's going to solve them is and Sam, or not Sam Altman, but Jensen Huang identified this correctly. Right? He realized that the reason that the cost of compute eventually tends towards zero is because the utility outweighs the cost. In all cases, as AI gets smarter, it only produces better solutions that outweigh the cost of producing those solutions on an exponential scale. That's one of the differentiators, right?
Is that like Moore's law, where things get better over time?
Wang's law.
What is it?
Jensen Huang, CEO
Wang's law
of NVIDIA.
Yeah.
Wang's law is that the eventual cost of inference drops to zero as utility increases.
Oh.
Right. So there's a as the utility goes up, cost goes down. Okay.
Is there a peak cost where things are?
We're in the peak cost, and then it gets cheaper from here. Okay, as utility goes up, and eventually that plateaus when cost reaches zero. Right.
So it's a trend that's skewed to the left.
Yeah, it's a race to the bottom, like telephone companies. Remember telephone companies?
Interesting. Yeah.
Same thing, right? Inference companies are in a race to the bottom. They have to continually make their tokens cheaper, because if they don't, their competitors will. They'll do so by increasing the efficiency of the models, by giving them more utility for less computing power. Period. Right? That is what AI model makers are doing. And if you don't participate in that race to the bottom, you're not participating in AI model making. So it is the bottom, right?
I'd like to interject here for a moment again, back to this idea of parallelism. So when we model the human brain, and a lot of analysis over the human brain, and that it appears to be very much a computer that acts in parallel. We have different specialized functions doing different things, and they're not happening, just one at a time, in a series of events and that, but they happen concurrently. So we could take, like consciousness isn't just like a singular monolithic thing, and that we can be conscious of all kinds of things. I am not conscious of what Austin has in his bathroom medical cabinet. Consciousness is limited.
Right.
And so with like the human brain and AI, attempting to model what we do every day, and that you're going to eventually have this parallelism, you're going to have specialized functions in that. And so this cost versus utility, going down, we're going to eventually be, not just have a cell phone, but have a backpack that we're packing around that's going to help inform us about the world,
right.
And it'll be just as ubiquitous as a cell phone.
Correct.
Augmented reality is going to be, very realized, is what I see.
Right.
It'll be like having a parrot on your shoulder that's smarter than you are.
Edge computing is called. Every device in your house becomes a target for inference, right? It becomes a target for increasing the intelligence of the network. Can we run inference on it? Then it can increase the intelligence of the network. Every Alexa, every smart appliance with a CPU in it can participate in increasing the intelligence of the network. That's edge computing, right?
Wow.
You know what? Have you ever seen a little film called Idiocracy?
Mike Judge, of course. Did you know?
I actually know Mike Judge personally. I went to school with his nephew, who coincidentally is also named Austin. We went to school together, but it's one of his works that I love most. I love everything he's ever made, but that movie is phenomenal. It is so
Most
insightful,
prophetic movie ever. I
scary,
mean, it's just like,
prophetic.
oh my.
I used to run a game called Syndome about a cyberpunk future, text role playing, and one time somebody came through character creation, and for some reason they typed in "not sure," which is the famous scene in the movie in which he goes, I'm not, and he goes, your first name is not, okay, and he goes, I'm not sure, and he goes, okay, not sure, and then he becomes not sure for the rest of the movie, right? And so we cracked up for hours when somebody accidentally came to character creation as not sure.
Yeah.
I just love the intellectual couple on the couch, and then the basically the crazy people in the cabin or the trailer.
Yeah.
And that just defines my entire relative sphere. And my sons are like these intellectuals, and they didn't reproduce, so I don't have any grandchildren because it just wasn't the right thing. And it's just, oh my God, this is really happening, isn't it?
I understand. People can continue to hate AI, and then they continue to. Then what they'll do soon is they'll use AI to find new solutions about how to hate AI, and the cycle will be complete. I'm done. Mic drop. Right. That's all I can say. Right.
So, what advice would you give to young students who are interested in pursuing a career at the intersection of computer science and biology? Do you think there will be anything for them, or is AI going to squeeze them out?
Oh, there's so much. I mean, you need to learn two things: CPU design and molecular geometry. Not just molecular biology, molecular geometry.
Yeah.
Why 108.5 degrees? Why? What is the nuclear force and the magnetic force doing there? What's going on? Why sp2? Why? Ask the question why. Then ask the question, and this is the thing, when I interview people, I have interviewed people all my life in order to hire. When I interview coders, right, I ask them a question. I say, there's two things I'm looking for. Number one is a good answer to my question. I'm going to type www.google.com into my browser. I'm going to press enter. What happens? Okay. Now, an average coder will say something like, well, you're going to make an internet request to, Google's browser, Google's machine. I'm going to go, bye, right? You're out of here, right? Here's what I'm looking for. I'm looking for you to say, when you press the enter key, an electrical signal goes, connects from the switch in the keyboard to the USB hub. The USB hub then hits an interrupt pin on your CPU. The interrupt runs a piece of code, yada, blah, 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 DNS, TCP/IP, UDP in there, doing up the IP lookup for the DNS address. Then we get to the TCP/IP connection. How is that structured? And then we can finally talk about maybe HTTP as the protocol, HTML, the rendering engine, all of that.
Oh, good. I understood like 60 to 70% of that.
That's what I'm looking for.
I got 100%.
I'm looking for them to understand the whole stack. CPU design will teach you the whole stack. You will learn the whole stack along the way. Then learn web design. You're going to need that too, and AI in Python. Meanwhile, learn how to make chemicals fall into lower energy states and create more complex macromolecules. Learn how to turn that into an assembly line through autocatalytic chemical reactions. Learn about systems chemistry. Learn about statistics. Learn about how the intersection of computer science and biochemistry comes together through statistical inference. Molecular.
Well, I'm taking chemistry and statistics right now, so I'm on the right track.
Molecular geometry asks the question, why molecular biology? Right?
I'd like to interject here for a moment. And let's look, for example, the nature of carbon. And it's tetrahedral shapes. Now, the guy who first proposed the tetrahedral electron configuration of carbon, he received his Nobel Prize posthumously for stating that, because according to current theories of the time, it was not going to be that shape at all. But it turns out nature is lazy. Nature is extremely lazy, and this is what drives molecular geometry. So if somebody's to come up to you and say why, you tell them nature is lazy. It's not going to do any more work than it has to.
Right.
And if you want
energy
to,
can be hard to come by.
yeah, and here's I'm going to go back to the pet peeves about creationists and their arguments, and that they'll say, well, you can't have order from disorder. You can't have this from this and that. It's energetically unfavorable, according to thermodynamics. But it turns out that living organisms contribute to the overall increase in entropy of the environment overall in that. So it's not breaking anything. I
Yeah,
mean,
because
we got crystal formation and
they
everything.
take in and use materials and expel waste, basically, right?
Right.
Yeah, and this is what drives reactions too. I mean, just in the formation of water in that. Water is very lazy. It's so happy where it's at. It takes an enormous amount of energy to split water in that, because it's so energetically favorable in that form, and that's what drives molecular geometry. And it goes back to the Pauli exclusion principle. It goes back to we can't take energy out of any process whatsoever, and reaching this lower state of energy and this higher state of entropy, that's what's driving all of it. They're looking for a magic bullet. We hand it to them and we get an
Yeah, and that's the thing is same thing with like when you learn CPU design, you learn all the other stuff along the way, right? Same thing with molecular geometry, you learn thermodynamics along the way, right? It's one of those things you have to pick up. It's a prerequisite, right? And so this is the path that you end up on anyway. And if you don't get this stuff early, you're gonna need it later, and you're just gonna be missing it, right? So go study CPU design. Go study von Neumann and non-von Neumann architectures. That's where the real interesting shit is, right? Is in rethinking what a CPU is, especially in terms of what if we made CPUs more biological, more like machines that are chemically based? What if we gave them some of the same attributes and behaviors and could we get some work done that way? Turns out, yes. Turns out evolutionary computational frameworks are a thing. You don't have to be a chemist to be in the intersection of computers and biochem. It's not necessary. You can do all of your work behind a keyboard and still make great amounts of progress, right? You really, really, really can. So, learning how to do this stuff, like, I don't have chemicals in my house, but you pick up the process along the way. It's critical to understanding it, right? So I'm a coder who happens to have an intersection of biochem, right? And that's a great place to be, in my opinion. Somebody who knows how to take Python and deploy it to a GPU cluster has a home in any modern biochem research lab, period. Right?
Really?
Absolutely.
Yeah, I need a home. Anyway. Yeah.
You know what? I can't imagine a better thing to end the stream on. I love everything of what you just said so phenomenally. Let's start wrapping it up. If everybody's happy with wrapping it up there, I certainly am. T, give us some final thoughts. Tell us where we can find you if we want to, collaborate more in the future and whatnot.
Absolutely. I've got a new project now that I'm working on. So if I could just plug that really fast, that would be all right. Cool.
Yes.
So I identified that as a coder, I do a lot of research using AI. It's one of the things that, you end up with a problem And the AI, of course, doesn't have in its memory how to solve the problem, and so it needs to do some web research. The problem is that that's a tricky process. A lot of the times it's got to look at a number of different places. Sometimes it gets the answer, sometimes it doesn't. What's needed here is an ever-evolving knowledge base, and that's what I'm building now. It's called ToolStack. That's TOOLSTAC, without the K.com. And what we're doing is we're working on an international, across 9 different languages, ever-evolving knowledge base of technical articles, long form, well-researched, and constantly being updated by gap analysis and market analysis, and of course, user queries. So if you're a developer, I definitely invite you to check out what we're building at ToolStack. We're not quite ready for mass amounts of traffic, but you can definitely come and see sort of what it is that we're building. We've got our articles up, and we're working on making it more AI friendly and getting it ready for mass AI citation. Because
can you see the live chat, T?
Oh, I can't at the moment.
Toolstack.com, TOOLSTAC.com, right?
Yeah, that's right.
Got it.
Yeah,
I put it in
right.
the chat for everybody.
And then,
Oh, you got a link?
Yeah, if somebody could put a link there, that would be great.
I got a link.
I put down the web address. I don't think it turned it into a link. Let me try again.
Okay, so
No, I got the link, Austin. Don't worry.
So
It's
my
already
point
up.
is, if you're a developer, you can follow us on Twitter. That's toolstack_com. And what we're doing is we're trying to build for the citation economy that has not emerged yet. Because we believe that traditional SEO is dead. Humans aren't browsing the internet anymore. In the future, AI citations are all that's going to really matter. So that's what we're building.
Cool.
What I'm building anyway.
Awesome. Oh, we lost Austin. Every now and then Austin drops out. So
Anyway, if you come back, you'll see we're about a content velocity of 130 well-researched articles that are between 1,000 and 3,000 words with heavy citations.
What kind of articles?
Technical articles, how-tos, tutorials, comparisons, reviews, just to overall troubleshooting guides, things of that nature. And so what we're trying to do is we're trying to build a comprehensive developer resource that is completely up to date and market driven. It's for AIs to do research on, so that they have a resource to find solutions to problems.
Yeah. God, I've used AI for bioinformatics, like using the UCSC genome browser and NCBI. And I was stuck for years and years trying to use them damn tools because the documentation sucks so bad. And AI just shot me forward, like light years. It's unbelievable.
Unreal as done for productivity. Right?
But it'd be cool to have a really good knowledge base based on just that bioinformatics tool set right now.
One that is constantly being updated.
Right.
You changed at a velocity that is, that major news publications can't even touch, right?
Yeah.
So that's the power of AI, is to do things that create massive data moats across 9 different languages. And there's a differentiator. If you think that Russian hackers don't use Docker, they need their content in Russian. And what's more is there's no point in translating the material. So we use language moats. When we develop Russian content, it's targeted for Russian nationals. It's targeted not for tax, USA tax versus TurboTax. It's targeted for C1 compliance in Moscow with Bitcoin.
Yeah.
And that's
I would like to,
right? And then this is the little Easter egg that we added. The 9th language is brain rot. Everything's
it's
written
what?
in Gen Alpha. Brain rot, Gen Alpha. It's all written.
Dog
water. He understood the assignment. And so we are targeting
dog water.
We are targeting a generation
Ugh.
who's about to come on the scene and write more code than the previous generation of coders could dream about.
Yeah.
We're targeting them with their language.
I would like to make my plug. Okay, I'm a Linux user, and I like local solutions as opposed to subscription-based solutions. And the problem that we're facing also with AI is this, AI through subscription.
Yep.
And it's taking it out of the hands of the common user in that it's a black box. We don't have access with it. We can't modify it. And that's where my only fear from AI comes from. It doesn't come from the AI itself. It comes from this forever subscription-based model.
Yeah.
Where you have the haves that have it, and you have the have-nots who don't.
But that's why
I'm paying for Cursor and ChatGPT right now at about $40 a month, and God help me if it goes up.
People can download their own currently today. Download their own large language models if they want to use them. And they're being developed in the free software foundation, and that so that your common man can have access to these without the subscription.
Well, that's the power of open weights, and why Mark Zuckerberg's scorched earth model is so powerful. Is when OpenAI and Anthropic come out with these closed models, and then Zuckerberg comes out with a just about as good model, but it's completely open source. OpenAI and Anthropic can't compete in that model any longer because everybody's going to prefer free over cost, right? And so that's why this whole endeavor is a big race to the bottom price-wise, is because they are competing in a market in which we just saw a brand new model from China with 1 trillion parameters that's open weight. That's game over, right? And it's competing at ChatGPT 4.0 levels and all of that, right? Which means that they're one generation behind with the open source stuff. And the only thing that's behind the gated gardens right now is the frontier models. And I think that's got to change. I'm with you. I don't think the frontier models can remain behind guarded gates. I don't think that works, right?
Yeah. Yep.
All right, and my final closing, I want to thank everybody who's been here watching. We've had like around 10 to 12 people watching most of the whole time. This is the perfect video with which to debut the new name for my channel. I changed it one final time. My channel is now officially called Scientific Origins According to Austin Sims. That way I can talk about all kinds of science and origins issues, and it's very broad and wide purview. And T, thank you so much for coming on and talking about like some core origin stuff, especially in terms of the scientific origin stuff. Very enlightening. This was one of the best streams I've done on this channel so far, if not the best. Thank you so much for coming on and regaling us with your knowledge and your experiences. It was so amazing. I enjoyed every minute of it. We got to have you on again sometime, man. This is you are such a phenomenal resource to learn from. And to everybody who watched and who watches the rewatch, thank you so much. Make sure you hit the like and subscribe if you're not subscribed already. Go like and subscribe to Mike. If you do, he promises to try and, produce something amazing before the final curtain.
Well, right. The final curtain. Yeah, subscribe soon because I'm gonna die soon. So I'm really old, and I'm back working on chromosome 2 fusion, and I'm hunting up the centromeres right now. So
that's amazing.
So,
yeah, I'm also an engineer and pushing 50, and you know what happens to engineers when they reach 50, don't you?
You take them out behind the
yeah,
barn and
shoot them. Yeah. Well, I'm 74, so you can imagine. You can imagine where. So when I say what you mentioned about CPUs and understanding CPUs, I got into it when the 8080 just was produced, and 6502 and 8080. And the first thing I did in electronics was figure out how CPUs worked, because I didn't believe they could work until I understood them. But it was pretty cool to figure out the gates and the latches and all of that shit. And I worked in that stuff for about 5 years.
And
So,
we owe all of this to vacuum tube technology and
Absolutely.
all
oh
the
yes,
analog work,
vacuum
all the
tube.
analog work in the 20th century.
Yeah, but I
Yeah.
encourage every single software engineer, just because they feel like, hey, I'm a software engineer, to go design a CPU and code with at least 30 opcodes, right? Just a weekend project. Like literally hack it out just to see if you can. Just to see if you understand the idea of decoding and executing an instruction.
Yeah.
It's one of those things that if you I mean, and this is how I learned. This is the final thing I want to add, right? Is I learned at a time in which we didn't have the internet. We had to walk uphill in the snow both ways, right? Barefoot. Downloading Frack magazine from BBSs. Okay. And what I would do is I would read an article, and I did not understand what I was reading. I read Smashing the Stack for Fun and Profit, one of the most famous frack articles ever. I highly encourage everyone to read it, especially if you don't understand it like I did, because what happened is they were talking about CPU registers. And I didn't know what a CPU register was. Okay? And then I read another article on the VAX VMS, a computer I have never touched in my entire life. But I read the article anyway. And what it did is it talked about how registers are dedicated pieces of memory that the CPU can do operations on. And the light bulb went off.
Yeah.
And I was, oh, they were talking about that back in Smashing the Stack for Fun and Profit. And I got a little bit smarter. Just like my friend Destin from Smarter Every Day. I encourage everyone to get a little bit smarter every day, because that's the type of thing is reading an old frack article about an architecture that you will never lay your hands on, that gives you the insight into fundamental architectural design that will take you farther than anything else.
I posted a link to a Amazon book, a really old book on the 8080 logic design. That really, it's by this guy named Adam Osborne. I met him; he's a real dick, but he wrote a wonderful book on CPUs. And at the 8080 level, right, the old first microprocessors, that is a good entry level. You wouldn't want to enter what's happening today.
So, you don't have to get into 486 real mode. Don't.
Yeah,
No.
right. Yeah, 8080 is good. Yeah.
No, and I mean, like,
anyway,
I have one tattoo. It's of an 8080 on my shoulder.
Oh, really? No shit. Wow.
8088 actually.
Yeah, well, I got out of treatment for alcoholism, and I came home, and my wife had a popular science book with a picture of the 8080 processor on it in 1974, and that was the beginning of my career right there. Just that one article that they did on it, and that was the entry. And from there, it's been a wonderful ride.
Anyway. Hey, Seth, the ambushed apostate. How's it going, my brother? We're actually just wrapping up here. We finished all the science topics, and now we're just kind of shooting the breeze about life a little bit, and giving you one more final lesson before we go out, basically to be open and be super curious, and to put a bunch of energy into your intellectual pursuits, and maybe you'll be able to retire early like T here has been able to do, because mad props, man. Good job on everything you've accomplished, and thank you so much for coming on my channel. And yeah, go back and rewatch, Seth, and enjoy. It was a great conversation. Thanks everybody for watching. Any other final comments, or shall
have
we
one.
close it out?
Yeah,
I have
right.
one.
Go
Let's all have a Vulcan mind meld in that, and thank our Lord and Savior in electricity, Michael Faraday,
Right.
and
Right.
be
Okay.
glad that he's born. Otherwise, we wouldn't have this,
Yeah.
any of this.
Oh, all right, y'all. Have a good one.
He-
Thanks for stopping by.
By Grabthar's hammer, I will avenge you. Never give up. Never surrender.
Live
Uh,
long and
Galaxy
prosper.
Quest.
Galaxy
All right.
Exactly. Yes.
Let me know when we're out.
Yep. Leave them wanting more.
Bye, everybody.
Bye.